Every video this week is going to be on conformational analysis, which has everything to do with how a particular molecule is kind of oriented in space. So just as like a quick example here, you'll notice that the different conformers of ethane are possible by rotation about this bond between the two carbons. Right? And so what we're going to be learning today, and we'll get more and more complex as we go through the week, until we end with what's called disubstituted or multi-substituted cyclohexanes. But we're going to start nice and simple here with ethane. And you'll just have to apologize my Sasquatch hands. I couldn't figure out any easier way to kind of do this video. So the first thing that we need to know about ethane is that there are really two major conformations that we need to talk about. The first is what we call eclipsed ethane, right? And so you can kind of see why we call it eclipsed, because if you sight directly down that carbon-carbon bond, you'll notice that all these hydrogens are eclipsed. And it turns out that there's an energetic cost to this, what's called an eclipsing interaction between two hydrogens. And what we're going to learn is different ways to represent different conformers of ethane. We're going to learn about like various energetic costs, and then we'll kind of work in some energy diagrams. So if you notice me rotate about 60 degrees about that carbon-carbon bond, you'll notice that now all the hydrogens are staggered. This is, not surprisingly, called staggered ethane. So really what we're doing in what I'm about to show you is we're just rotating about that bond, and we're alternating between these two forms of staggered ethane and eclipsed ethane. What are some different ways that I can represent this with structures? Well, one is called the sawhorse way of representing ethane. This one is something we're going to use a lot more when we get to cyclohexanes, but for now you can just kind of bear with me the way that I'm going to represent this eclipsed cyclohexane, and then we'll work to something called Newman projections that are a little bit more specific. So here we have sawhorse ethane. And you'll notice that this is kind of representing the structure I hold in my hands, and we're kind of holding it at a little bit of an angle, really. And as I said, this is not as important to be able to do than when we get to cyclohexane conformers, and you'll see what I mean by that in Wednesday's lecture slides. But the way that we're going to represent this is through what's called a Newman projection. That's the most common projection that you're going to be using when we talk about conformational analysis, at least of simple organics like this. So how do we do that? Well, first of all, you'll notice that I'm holding the model kit, sighting along what's called the C1, C2 bond. And all I'm going to do is I'm going to draw the orientations of my hydrogens like so, and this carbon right here is going to correspond to that very front carbon. And then the back carbon I'm going to represent with a circle, and then I'm going to just kind of, not twist, but kind of like alter the projection just a little bit so that we can kind of see the H's on that back carbon. Because obviously if I drew them directly over the other ones, we couldn't see them. So this is called a Newman projection. And Newman projections, usually I used to learn to just kind of hold one thing constant, and then I would rotate the other thing. So what we're going to do is that we're going to keep the back constant, and we're going to rotate around to staggered ethane. And I'll show you the results of that and what the Newman projection looks like, and also the sawhorse model in just a second. So here are the two staggered ethane conformers. One is the sawhorse and the other one is the Newman projection. Some things that we should talk about here is that often this angle right here between hydrogens on adjacent carbons, this is something called the Dihedral Angle, which is often abbreviated with a phi. So this angle right here is equal to 60 degrees. And the other thing that we need to talk about, well, by the way, the dihedral there is 0 degrees. So essentially what you're doing is, if you imagine taking a circle and dividing it into 3 equal halves, you've got a 120-degree bond angle between hydrogens, at least when you look at it in kind of a flat fashion. And then we rotate to the staggered by going to 60 degrees. We'll get back to the eclipsed if we rotate by a full 120 degrees. Then we do another 180 degrees. You get the idea. But the important thing about conformational analysis is you don't just write the molecule. Usually you talk about the energetic costs. And so there is an energetic cost to having this kind of interaction right here. Maybe I'll switch to a different color so it can be highlighted a little easier. So it turns out that there is an energetic cost to any time you have eclipsed hydrogens. So here are all my eclipsed hydrogens. It turns out every single one of those eclipsing is called torsional strain. And torsional strain has something to do with the fact that the lone pair of, the electrons that are shared between this carbon and hydrogen right here, and the lone pairs that are shared between this carbon and that hydrogen right there, they don't really like to be eclipsed like they are right here. So that creates a certain amount of kind of a twist, hence the torsional strain that you guys have had physics. No, torsion has something to do with kind of a twisting force. And it turns out each one of these interactions is just about 1 kcal per mole. Those of you folks that have had physics before, you're probably more used to the joule or the kilojoule. In organic, it's kind of a funny thing. We always use these non-SI units called kcals. The good news is that it kind of makes it easier for us to remember various interactions because they're often in whole numbers. So this entire structure, if you count up all the different torsional strains, it turns out that there are 3 different 1 kcals. So what this means is that eclipsed ethane is just about 3 kcals per mole. I guess I could fit that in here. Sorry, it's so smushed. So the overall cost to being an eclipsed ethane is about 3 kcals per mole. And in staggered ethane, there is no cost. So that's going to allow us to draw the following energy surface. Here's just an abbreviated energy surface here. And what you can see is, at least the way that I started us off here, it kind of resembles a cosine wave. And what happens is that, as we rotate along that dihedral, you'll notice that our energy goes down, and then the energy goes back up, the energy goes down, and it just has this repeating pattern. And of course we could go 360 degrees if we wanted to. In fact, I think in your book it has this. But the important thing to know is that the total distance between these 2 energetic points, the distance between the trough and the peak, that is equivalent to just about 3 kcals per mole. Right? And so the reason that this has an importance in organic chemistry is one of the things we're going to start to realize is that the 3-dimensionality of organic molecules is really important. And this helps us to kind of analyze different situations and make good predictions. For instance, the reason that the high octane gases, for instance, they burn so hot is that you're relieving a lot of this kind of these conformational analysis type negative interactions by burning it and turning it into just carbon dioxide. So anyway, this is just kind of something that we're going to have to discuss. And we are going to skip propane and we're going to go directly to butane because it's the very prototypical example. And it's also going to allow us to highlight a couple of important things, most important of which is what's called a Gauche interaction. Okay, so let's talk about these butane conformers. First of all, you notice that there's a whole bunch of carbon-carbon bonds that I could potentially cite down in the Newman projection. It turns out the most useful one is the one between C2 and C3. So this guy right here is C2, that guy right there is C3. And so what we're going to do in our Newman projection is we're going to cite down it like that. And you'll notice here that I started with what's called the fully staggered conformation. Or some people call this anti. And what you're referring to is the position of these big, giant, bulky CH3 groups. If they're positioned on opposite sides, like they are here, when I kind of, turn it to the side, you can kind of see that a little bit better. It turns out that this is the lowest energy conformer, and it has no appreciable energetic cost to the molecule. So when I draw this, notice what I'm going to do. I am going to use that same exact kind of pattern for the Newman projection. Right? And so that obviously corresponds to the front carbon. I'm still going to put the back carbon in there. And at least for the hydrogens, everything is going to look the same as it did in the case of ethane. But now we need to indicate the CH3. And a lot of people think, oh man, what am I going to do to kind of draw this properly? Basically, you just group everything else as a big giant group. In fact, if this was a bigger thing than a CH3, typically all you do is you just draw like a big giant condensed structure for what it is, right? And so in conformational analysis of even complex molecules, you kind of go on a case-by-case basis. In this particular case, we're going to highlight all the important things in butane. So this thing is called anti, or you can also call it fully staggered. That's probably a little bit less. Oops, sorry, I'm tilting this to the side. Fully staggered. And as I look at staggered, I have no idea if I spelled that right, so sue me. So this guy, the overall energy difference, we're going to call that 0, right? We just kind of, we're going to put a 0 on our scale right there. Okay, so just like before, we're going to keep the back the same, and we are going to rotate 60 degrees. And one of the things you'll notice when I rotate 60 degrees, you'll notice that I now have an eclipsing interaction. And not only that, it's not just between two hydrogens. Oh, I should mention I didn't put any hydrogens on here because I ran out. You'll notice that this CH3 group is much bulkier, right? This has more of what's called a steric presence, right? It's bigger and bulkier, more spinach or junk in the trunk, or whatever you want to call it. So before, this was about 1 kcal per mole when it was 2 hydrogens. Now this torsional strain is going to get a lot greater. So let me draw the Newman projection, then we'll label a couple of things. Okay, so what we'll notice is that we've got our old HH eclipsing interaction, which is worth 1 kcal per mole. And you'll notice that we now have 2 new eclipsing interactions that we haven't seen before. And just because it's a little easier to write with this marker, I think I'm going to write with this marker instead. And the cost of each of these is 1.4 kcals per mole. So one of the things that you'll notice is that it's a pretty good amount worse of an interaction. So what we would do in this thing, which we're going to call partially eclipsed butane, if we add all of these up, we end up with a total energetic difference. I guess I'll put it up here because I put the other one up there, of 3.8 kcals per mole. My units are I'm kind of squeezing everything together, so the units are going to have to be left off of that number. Don't tell any physicists that I did that. So you can see that that's, if we were to use the Arrhenius equation back from Gen Chem, we'd notice that there's a pretty good likelihood that this form is going to be in like a room temperature sample slightly more preferred over this guy by a pretty decent margin. And of course, we're going to keep playing this game, and in the very next structure, I'm going to use an entirely new sheet because we're going to get to highlight something called a Gauche interaction. So here we have Gauche butane. The reason that we use that word Gauche is because anytime you've got this 60-degree dihedral angle between CH3 groups, or honestly, not just CH3 groups, but any bulky group, This is called a Gauche interaction right here. The energetic cost of this is relatively high. It's 0.9 kcals per mole. You'll notice that it's not quite as bad as the torsional strain from an HH eclipsing interaction, but it is significant in that, you know, it is something that the molecule would like to relieve if at all possible. And so just to make sure that we're all kind of on the same page here, let's rotate everything so that we can actually see that Gauche interaction. There it is. You'll notice that it's just kind of put these CH3 groups kind of, you know, slightly too close to each other. There is an energetic cost. And so if we continue it, you'll notice that we go from Gauche butane to something that looks really, really ugly. In fact, if you were to build a model kit of this, you hear kind of a thwacking. That thwacking is the sound of a steric interaction, right? Which is really, really, you know, we'll say something that molecules will try to avoid. So let's see that on the very next Newman projection. So here's fully eclipsed butane, and you'll notice that the interaction we were just talking about before, the eclipsing from those two CH3 groups causes just about 2.4 kcals of additional strain. So, oops, I forgot to add up the energy of our Gauche butane here, so I'll do that in just a second here. So you'll notice that the torsional strain, due to different types of interactions, have different kcal values. We know that each one of those HH eclipsing torsional strain energies is right about 1.0. So if you look at this form of a fully eclipsed butane, you're going to notice that the energy is about 4.4 kcals greater than the anti-form of butane. So let's count up over here the different Gauche interactions, and you'll notice that in this particular case, there's no energetic cost to anywhere else in this molecule. It's just the Gauche butane interaction. So we're going to call this 0.9 kcals per mole. So we've pretty much been through everything. The pattern just repeats, obviously, as we continue to rotate this thing around. Eventually there'll be another Gauche interaction, and we'll go through another partially eclipsed interaction. We'll keep going. But I wanted to show you what this looks like on the energy surface. This is my very ugly attempt to show you what the energy surface does here. So a couple of things to remember is that this highest energy fully eclipsed state, I gave a dihedral angle of 0. And then you notice that I went down to Gauche butane here, which is kind of what we would call a local minimum. And so this is fully eclipsed. Up here, we go down to local minimum for Gauche. We go back up when we get to the partially eclipsed. Oh my goodness. And then, of course, we've got the global minimum, which is anti. And honestly, this should be symmetric about like a y-axis line, but you know, you get the idea. And so what we're going to kind of build towards is getting slightly more complex molecules. And obviously you can see what happens just with butane as we rotate around here, which it might be helpful to kind of go through the full analysis here. So I'm sighting down C2, C3, right? There's my 4.4 kcal fully eclipsed conformer. Then I'm going, I guess it depends on how I rotate this thing. Let's just rotate it this way. Then I go to my Gauche. I keep going. Eventually, I get to partially eclipsed. Then eventually I'll go to anti. And then you notice that it just kind of keeps repeating as I rotate this thing around. So obviously this only has, one major site along this bond of any kind of like torsional interaction or steric interaction. But if I had other groups out here that, even in simple alkanes, we would have to also consider those. And we would do a Newman projection where we sighted down that particular bond and, count up all the energetic contributions. And so this conformational analysis thing can get pretty crazy. But for our class, what we're going to do for class on Wednesday, we're going to take a look at a cyclohexane, and we're going to start to kind of do a conformational analysis on those, because those are really the questions that give us the most insight to what's going on in organic molecules. So if you don't have a model kit, as I said, I have a site that is kind of like a good free site for you. I really recommend, if you haven't done it yet, to grab yourself a model kit, because a lot of this stuff, especially when we start to look at cyclohexane conformers and eventually go into talking about stereochemistry, is going to be really helpful for you guys if you have one of these. All right, take care.